Okay, this is lesson 14, graphs that represent situations. Our lesson objective today is to explain how a quadratic equation and its graph relate to a situation. So we'll start with the warm-up, 14.1, a jumping frog. The height in inches of a frog's jump is modeled by the equation h of t equals 60t minus 75t squared, where the time t after it jumped is measured in seconds. Take a minute, pause the video, try number 1 and 2, and press play when you're ready to check your work. Okay, so if you calculated h of 0 and h of 0.8, you would find that both of those values are equal to 0. And so that means that the frog is on the ground when t equals 0, or before it jumps, and when t equals 0.8, which would be when the frog lands back on the ground after its jump. And so those both represent when the frog is on the ground. Right, so the h of 0 being before it jumps, and after it lands back on the ground. Question 2, how much time after it jumped did the frog reach the maximum height? Explain how you know. And so here we can say that the frog reached its maximum height at t equals 0.4, because that is the halfway point between 0 and 0.8. And so if we were to graph the function, the vertex of the graph would have a horizontal coordinate, or in this case the t-coordinate, of 0.4. All right, in 14.2, we have a catapulted pumpkin, and the equation h equals 2 plus 23.7t minus 4.9t squared represents the height of a pumpkin that is catapulted up in the air as a function of time t in seconds. The height is measured in meters above ground. The pumpkin is shot up at a vertical velocity of 23.7 meters per second. Now for number 1, you might want to actually jot a couple quick notes down and consider the questions. What do you think the 2 in the equation tells us? And what about the negative 4.9t squared? If we were to graph the equation, would that graph open upward or downward, and why? Where do you think the vertical intercept would be? And what about the horizontal intercepts? Remember the vertical intercept being our y-intercept, and the horizontal intercept being our zeros or our x-intercepts. So take a minute and at least consider those questions and maybe jot down a thought or two about those. Okay, so hopefully you came up with a couple of ideas as you went through and were able to jot down just at least a couple of notes. For, let's call this one A, what do you think the 2 tells us? Well, in this case, the 2 tells us that the pumpkin would be 2 meters above ground before it's lost. So it would be 2 meters above ground before they launch it. And that would be the pumpkin. And the negative 4.9t in this case, that shows us the height that's lost due to gravity. So that's basically the effect of the pumpkin's height from the gravity. And so how that gravity is pulling the pumpkin back down. If we were to graph it, in this case, we should be able to tell that it's going to open downward. And that's because the coefficient of our squared term is negative, right? It's a negative 4.9, so we can tell that it's going to open down. Where do we think the vertical intercept would be? This case we should be able to tell because the function's given to us in standard form, and so we could say that the vertical intercept would be 0, 2, because we can see that right there in the function. Now the horizontal intercepts are going to be a little harder to tell without graphing. So let's take a minute and graph our function in Desmos and see what we come up with. Okay, so we have, say y equals 2 plus 23.7 minus 4 point, oops, I forgot my x squared. Okay. And so this parabola here is modeling the height of the pumpkin that was catapulted. We can see that we have our vertex or our max. We can see our y-intercept is in fact 0, 2, and we can also see those x-intercept, or those zeros of the function here. Okay. Let's jump back over and look at 3. So if we identify the vertical and the horizontal intercepts, we saw that the vertical intercept was 0, 2. The horizontal intercepts, or x-intercepts, were about, where were they? I think it was around negative 0.8. Oops. And let's just go back. Yeah, about negative 0.08 and about 4.92. Okay, and if we want to explain what each point means in this situation, the vertical intercept, that tells us the pumpkin's initial position, before it being launched is about 2 meters above the ground. And the positive intercept, in this case, tells us that the pumpkin hit the ground after about 4.92 seconds. After it was launched. Again, in this case, we could say that that negative intercept is meaningless. It doesn't have any value for us in this given situation. The last thing that the question had asked us to do was to determine the vertex of the graph and then explain what that means. And so we can see that the vertex here, if we go back onto our graph, that is going to be the max in this case, and it's about 2.4 and 30.7 if we round. And what that means is that the pumpkin reaches its maximum height which is about 30.7 meters at about 2.4 seconds. All right, so just for that last one, remember that the graph shows us two horizontal intercepts. We have one that was positive and another one that was negative. And in this case, we decided that the negative one is not meaningful for us because it's implying a negative value of time or time before the pumpkin was launched, which in this case is not relevant in this model or this situation. Okay, in 14.3 we're looking at the flight of two baseballs. Here is a graph that represents the height of a baseball, h in feet as a function of time, t in seconds, after it was hit by player A. So we have this one that's going to be representative of player A's baseball. And so we're given a graph here. The function g is defined by g of t equals the quantity of negative 16t minus 1 times the quantity of t minus 4. And that also represents the height in feet of a baseball, t seconds after it was hit, in this case by player B. Without graphing, function g, answer the following questions and explain or show how you know. So in this case, you're going to have to really reason by comparing a graph for player A to an equation for player B. And so it's going to be a little difficult to do that, but what you should think about are what things can you figure out from each of these, such as our x-intercepts, our vertex, our y-intercepts, and any other information you think is relevant to help you figure out this problem. So take a few minutes, see if you can figure out 1, which player's baseball stayed in flight longer, 2, which player's baseball reached a greater maximum height, and 3, how can you find the height at which each baseball was hit? And remember, you're comparing the graph for player A to the equation for player B. So pause the video and press play when you're ready to check your work. Okay, so for number 1, which player's baseball stayed in flight longer? And so what we want to figure out here are what are the zeros of both of these functions, because we want to see how long it stayed in flight. So we want to know when does it actually hit the ground, and that is going to be the zeros of the function. So we need to, the key here is that we need to figure out what the zeros are. In our graph for player A, we can see that the 0 is at about, looks like just a little over 5 seconds. So we know that for player A, it is in flight for about like a little over 5 seconds. And then for player B, we have the function, and so we can use that to find our zeros. And so we can look at negative 16t minus 1 being equal to 0 and t minus 4 being equal to 0. If I solve my first factor, I'm going to get negative 1/16. And so in this case, right, we don't want a negative time, so that's not going to be meaningful. But I see my second one is t equals 4. And so that means player B's baseball stayed in flight for about 4 seconds before it hit the ground, and player A's stayed in flight for about a little over 5 seconds. And so in this case, player A's baseball is going to stay in flight longer. For question 2, we want to know which player's baseball reached a greater maximum height. And so in this case, we're looking for the vertex of the parabola. So for player A, we can go back to our graph and we can see our vertex is around maybe about looks like about 2.5 and about 105 feet. So we can say that player A's baseball reaches a max height of about 105 feet based on our graph, And then we can try to figure out what the max would be for player B. Now, when we try to find player B, we know the vertex of the graph is going to have a t-coordinate of halfway between our two zeros. If you remember, our zeros for that from part A or part 1 were negative 1/16 and 4, and so we can estimate that that's going to be halfway between that is going to be at about when t equals 2, and then we can plug that value in for t equals 2 into our equation and solve. So we can actually figure out that g of 2 then, right? So what is player B, what is the height of the ball at the vertex, which would be when t equals 2, and we can say negative 16 times 2 minus 1 times 2 minus 4. So we have negative 33 times negative 2. That will give us 66. And so then we know that the vertex of player B would be 266. So our height would be 66, and 105 feet is greater than 66 feet. So again, here player A's baseball is going to reach the greater maximum height of 105 versus player B's, which only got up to 66 feet. Okay, for number 3, how can you find the height at which each baseball was hit? So that's what we want to see here, right? We're looking for what are the y-intercepts. So if we go for player A, we can look back at our graph and we can estimate that it looks like just about maybe about 2 or so. And so we can look at the y-intercept of the graph. And if we want to find the height of which the baseball is hit for player B, here we only have the equation. And so, right, remember the y-intercept is what is the value when x equals 0. And in this case, we're looking, at t. So when t equals 0, we can find g of 0 would equal negative 16 times 0 would be 0, minus 1 times 0 minus 4 would be negative 4, and we would get that g of 0 equals 4, so my y-intercept would be at about 0, at 0, 4. So the height at which the baseball was hit for player B would be at 4 feet. Okay, so just to go back through, this was a lot of information when we were comparing both a graph to an equation, we want to think about a couple main things. So for number 1, which one stays in flight longer, right? We were really looking for the zeros, looking at the zeros of each function by either identifying them on the graph for A or by finding them from factored form based on our function. For 2, to figure out the maximum height there, we were looking at finding the vertex. And in this case, what was the value, the y-coordinate of the vertex. And for 3, to find how to find the height at which they were hit from, kind of that initial position, we were looking for the y-intercept, both on the graph and then using the equation for player B to find that y-intercept. All right, and so lesson 14 summary. We've looked today at a lot of examples of projectile motion, and we can model the trajectory of different projectiles, things like tennis balls or basketballs, or in an earlier case today, pumpkins, and we can model those using quadratics. Okay, make sure that you move on to your lesson cool down and or practice.